In this video, we will be reviewing the forces unit for the AP Physics 1 exam. We're going to start by talking about different types of forces, Newton's 3 laws, free body diagrams, and net force equations. To begin with, we have different types of force. To define this, we're going to define the term force as being a push or a pull acting on an object. So anytime an object is being pushed or pulled by something else, there is a force being applied. Some of the forces that we talk about pretty frequently, we have weight, which is also known as the force of gravity. We abbreviate this with a capital F with a subscript G, or we write it as a capital W. We also have the normal force. It's the force of a surface. Anytime a surface is applying a force to an object, we would refer to that as the normal force, and it always acts perpendicular to the surface. So you sitting in a chair, there is a normal force directed upwards to keep you from falling through the chair. When you're leaning against a wall, there is a normal force applied from the wall on your hand to keep you from falling through the wall. We're going to abbreviate that with a capital F and subscript N. We have a tension force. This is the force of a rope or a string. And we're going to abbreviate this F with a subscript T. Sometimes we'll just write it as a capital T. Be careful when you're writing a capital T, make sure it is straight lines and no curled lines, because that could be mistaken for a torque, a tau. Next force we talked about is the force of friction. This is a force that resists the motion of two objects. Specifically, it resists the relative motion of two objects between each other. So we're typically going to be working with what we call sliding friction. This is the force of friction that is acting on an object that is sliding across the surface, or when two surfaces are rubbing up against each other. There are two different kinds of friction that apply to the static friction, or the sliding friction. The first one is static, when the two objects are stationary relative to each other. And we also have kinetic friction, when the two objects are moving with relation to each other. The force of static friction is always going to be greater than the force of kinetic friction. We know this is true because if we were to measure the applied force versus the force of friction, as we increase the force we apply, we are going to increase the force of friction up until a point. That point is where the object begins to accelerate, and then our force of friction drops down because we've entered the kinetic friction realm. We also may refer to fluid friction. This is the friction of an object moving through a fluid like water, or more importantly, like air. Sometimes this might be referred to as a drag force. Our abbreviations for this are going to be a capital F with the subscript lowercase f, although sometimes we will write it as just a lowercase f. The next force we have is the spring force. It's the force a spring, S-P-R-I-N-G, force of a spring that acts to restore it to its equilibrium position. When you stretch a spring out, you're disturbing it from its equilibrium position. There's going to be a force applied through the spring to try to retract it back to its equilibrium position. We're going to abbreviate this capital F with a subscript S. Our next force is our pretty generic force. We have our applied force. This is a generic force, usually reserved for when a person applies a force to the object. Whenever we have a person applying a force, we're going to call that the applied force. If there is ever an instance where you're not sure what kind of force to call it, you're going to write it as a capital F and then give it a subscript that describes whatever it is you're trying to talk about. So if you're not sure what to call, let's say, the force that the engine of your car applies to accelerate your car, we could just call that F engine. Or if you're not sure what to call the force from wind pushing on a sailboat, you could call it F sub wind. Just use your subscript to be descriptive of whatever it is you're trying to describe the force of. This brings us to talking about Newton's laws. Newton's laws are by far the most important thing in this unit. They're one of the big three topics in AP Physics 1. Newton's laws, law of conservation of energy, and law of conservation of momentum are the three big topics in AP 1. The first law, an object in motion stays in motion. An object at rest stays at rest unless acted upon by an unbalanced force. This law is referred to as the law of inertia. Inertia being the tendency of matter to keep behaving the way it's behaving. So by that we mean the object is going to keep moving the way it was moving. This law states the equilibrium conditions when the net force acting on an object is zero, acceleration is zero, and velocity is constant. This law is one of the laws that students struggle with the most because we are so used to when an object has no forces acting on it, or when we think an object has no forces acting on it, it would slow down. But we have to remember that in the real world, there are always resisting forces like friction and air resistance that cause that negative acceleration. If we were to be able to get rid of them, if we were to be able to create a completely frictionless surface, an area with absolutely no air resistance, then an object that is moving will continue moving until something happens to it to stop it. The second law is dealing with what happens when we have an unbalanced force. An unbalanced force results in acceleration. First law, when the forces are balanced, there is no acceleration. Second law, when the forces are unbalanced, there is acceleration. When the net force is not equal to zero, it's equal to ma. The amount by which it will accelerate depends directly upon the mass. The third law, every action has an equal but opposite reaction. This law, the first and third laws are the two parts of this unit that students mess up the most. Every action has an equal but opposite reaction. You have to be able to identify your action-reaction pairs. It's not just when two forces are equal, they are action-reaction pairs. It is when one force acts upon one object, that object exerts a reaction force on whatever applied the force to begin with. When you push on an object, the object pushes on you. That is how sometimes you can be pushing on, let's say, a fridge, and your feet slide out from under you, because the force you are applying to the fridge is equal to the force that the fridge is applying to you. The reason that your feet slip out from under you is that the force of friction exerted on the fridge is greater than the force of friction exerted on you by the ground. So a classic question is, what is the reaction to the weight of an object? So I have an object sitting on the table. There is weight applied to that object. There is a force of gravity applied to the object. We have to figure out what the reaction to that is. A lot of times, students think that the reaction to weight is the normal force. And while an object sitting on the surface, a flat, level surface, weight will be equal to the normal force, they are not an action-reaction pair. The force of gravity of the Earth pulling on my object is reacted to by the force of gravity of the object pulling on the Earth. That is how we do action-reaction pairs. We just switch around the objects. So the force I push on the fridge is the force the fridge pushes on me. If I have a car that runs into a truck, the force that the truck exerts on the car is equal to the force that the car exerts on the truck. The next topic we have is free body diagrams. This is just a drawing that shows and labels all forces, not components, acting on an object. So it shows and labels forces, not components, acting on an object. So we need to draw all of our forces. We need to label all of our forces, and all of our forces are applied to one object. If we have multiple objects, we need multiple free body diagrams. So for an example, I have an object that's sitting on a surface. There is a gravitational force exerted towards the center of the Earth. There is a normal force exerted up. And I'm pulling on it with a rope that is at an angle. Let's say it's a 20-degree angle. There would be my free body diagram. I have each of my forces drawn as vectors. Each of them are labeled, and I don't have any components. What I mean by components is, for the same situation, I could have drawn normal force up, F applied in the Y, F applied in the X, and FG. This right here would be my components. Those are, while we use components to analyze this mathematically, we do not ever draw our components directly on our free body diagram. If you have something at an angle and you need to figure out components, do it separately. F applied, 20 degrees, F applied X, F applied Y. Always draw it separate, that way you're not going to lose points for drawing it on your free body diagram. Lastly, we get to all of the math. Now, when we went through this unit, we did spend a lot of time on the math, dealing with this equation, sum of all forces equals ma. When you're dealing with a situation that is accelerating, always set acceleration as the positive direction. You're going to have a bad time if you get your directions confused. If you have two objects that are connected and one of them is accelerating up and the other one's accelerating down, for the object that's accelerating up, up is positive. For the object that's accelerating down, down is positive. Our net force equation is always going to be equal to ma, although note sometimes A can be 0 if the object is in static or dynamic equilibrium. And we're always going to set it equal to the forces that make it move minus the forces that resist. What makes it move minus what holds it back. Now this equation here, if you have a situation that's two-dimensional, you're going to need to set that up two-dimensionally. Find the horizontal components and the horizontal acceleration. Find the vertical components and the vertical acceleration. A couple of equations that we need to know. Fg is equal to mg on the surface of Earth. And g equals 9.8 meters per second squared. You'll notice I'm not saying g is negative 9.8, because while that 9.8 is down, I'm always setting acceleration as positive. So if it's accelerating down, that's going to be a positive 9.8. The spring force equation is equal to kx. K being the spring constant, and x being how much it has been stretched away from its equilibrium position. And the force of friction, this is for sliding friction, is equal to mu times Fn. So we would need to find the normal force. Mu is the coefficient of friction. We could have a static friction, or we could have a kinetic friction. And the coefficient for static friction is always going to be greater than the coefficient for kinetic friction. Please note that if we are in this static friction regime, technically the equation is F, force of friction, is equal to is less than or equal to mu S times Fn. This is because if my object is not accelerating, then the force of friction is only going to be as much as I need it to be to prevent it from accelerating. One thing to note, when we're dealing with inclines, here we have our system. We have an inclined ramp, elevated at angle theta. Here we have our object sitting on the ramp. When I draw my free body diagram, I'm going to draw my gravitational force down. My frictional force would be resisting the motion, so it's resisting it sliding down the ramp. My normal force is perpendicular to the ramp. This angle theta will show up right here. That is how the angle to which I have elevated this is equal to the angle by which I have shifted gravity from being straight directly against the normal force. Now, you might be tempted to use a vertical and horizontal axes, but I would strongly encourage you not do that, because if this object is accelerating downhill, well, downhill is down vertically and to the left horizontally, and you're going to have it accelerating in both the x and y directions. Instead, rotate your axis to be parallel to the ramp and perpendicular to the ramp. Now, my normal force is in the vertical direction, my frictional force is in the horizontal direction, and only my Fg is in both directions, so only one force would have components. Also, I know this object is accelerating in this direction, so it's only accelerating in my new horizontal direction. So those are some things to keep in mind when you're going through your review for the forces unit of AP Physics 1.